Hello and welcome to this lecture, which is going to be a continuation of where we had stopped in the previous lecture. That was on a review on matrices. So today we will be talking about the eigenvalue equations. In this lecture, I'll be discussing eigenvalue equations. An eigenvalue equation looks like this. So A psi is equal to lambda psi. So over here, A is a linear operator. A is a linear operator which is defined over a with a domain and range which is defined over a Hilbert space. That means the Hilbert space is a vector space, if you recall, a vector space in which the scalar product is defined. Psi is a function in the same Hilbert space and lambda is a scalar constant. So what is the task here? The task is I want to solve equation number 1. And in equation number 1, there are some knowns and there are unknowns. This is what is known to us. The operator is known to us. And this, these two are unknown to us. That means, this is unknown to us. The vector is unknown to us as well as the scalar is unknown to us. So we want to solve this equation number 1 and find out what are these unknowns. So here, this psi is known as an eigenfunction, a function which solves this equation number 1. And lambda is known as the eigenvalue which corresponds to the eigenfunction. So some examples. Now these eigenvalue problems, they are extremely important. They appear everywhere in physics. So one example is resonant waves on a vibrating string. So this is an eigenvalue equation. How I get that equation? I get this equation like this. So let's say I have the restoring force, the expression for the restoring force. The restoring force is always opposite to the displacement. So if y is the displacement, then the restoring force will be simply equal to minus some constant into the displacement. And what is force? From Newton's second law, force is mass times acceleration, and this is equal to minus k into y. And now this I can take this m onto the other side, and what we left behind is a. And what is a? A is the second derivative of the position. A is the second derivative of the position. So this is equal to minus k by m. And what is left behind is y. So you can see here, this is d square by dt square, d square by dt square. It is operating on y. Okay, and when it operates on y, it gives us some scalar times y itself. So this is the operator. This is the operator. This is the operator a. This is the wave function psi, and this one is the scalar lambda. So you can see here a psi is equal to lambda psi. So this is an example of a eigenvalue equation. Another example could be the angular momentum of a rigid body. How this is an eigenvalue equation? You know that angular momentum L is equal to moment of inertia times angular velocity. Okay, so here I is a 3 cross 3 matrix. Okay, the moment of inertia is not a scalar, it's a tensor, it's a matrix, 3 cross 3 matrix. So now, since your L and omega, okay, L is parallel to omega, they are in the same direction. L is and omega, they are in the same direction. So it's because they are in the same direction, so we can say that L is equal to some constant times omega. L is equal to some constant times omega. So now substitute this back over here. So this gives us, on the right hand side we have I into omega, and on the left hand side we have L. So L is nothing but lambda into omega. So this becomes the eigenvalue equation that we have for the angular momentum of a rigid body. And another example is, of course, the time independent Schrodinger wave equation, the Hamiltonian operator. When it operates on a wave function, it gives us the energy times the wave function. So here, this is your lambda. So this is known as energy eigenvalues. Let me erase this. Okay, so now coming back to this. So we have a psi is equal to lambda psi. So here, as if you recall the previous lectures, so the A is the operator. Operators can be represented by an n cross n matrix. So we represent A operator A by an n cross n matrix, capital A. Then there is a vector. Okay, I think this is phi. I should not be using phi here. I should be using psi here. So it's my mistake here. This is psi here. Okay, so psi can be represented. This psi can be represented by a column matrix okay, or a row matrix. It's basically a vector. Then what are the elements of this A? Elements of this A, we can find the elements of this A in this way, using this scalar product. That means you take the scalar product of one of these psi, okay, one of this psi which is from the basis, and applying this A on another psi and taking the scalar product. So that is going to give us this elements of this matrix A. And the elements of X, the elements of this vector X, it is simply given by this same basis elements operating on psi, some basis elements operating on psi. So then this equation can be reduced to a matrix equation. This can be represented by the matrix A. This psi can be represented by X, lambda is as it is, and then this can be represented again by X. Okay, so the solutions of this equation, they are known as eigenvectors. So this X, this vectors X that we are looking for here, these are known as eigenvectors. So once an eigenvector is known, the corresponding eigenfunction can be recovered, and it can be recovered in this way. So now over here, suppose I have a squared matrix. In a square matrix, we call, there are some terms that we follow. One is the spectrum of the matrix A. The spectrum of the matrix A is the set of eigenvalues of A. Then the spectral radius of A is the largest of the absolute values of the eigenvalues of A. So let's say we have the eigenvalues, okay, the eigenvalues to be equal to 1, 2, minus 4, okay. So this set, okay, this set is the spectrum, okay, this set will be the spectrum, and the spectral radius, so what will be the spectral radius? It will be the largest of the absolute values. So what is the absolute value of 1? It's 1. Absolute value of 2 is 2. Absolute value of minus 4 is plus 4. Okay, so the absolute value, the largest of the absolute value, that will be the spectral radius. Then the eigenspace is a set of all eigenvectors which correspond to an eigenvalue A together with the zero vector which forms the vector space corresponding to this eigenvalue. Okay, so the eigenvalue equation is this: Ax is equal to lambda x, and this one, if you want to find out the eigenvalues, and from there you can want to find out the eigenvectors. So what you need to do is you take this onto the left hand side. Okay, so this you bring it onto the left hand side, and when you bring this, you get minus. Now remember, what we are actually doing is this: Ax, this is not algebra, okay, this you have to keep in mind. Ax is equal to lambda x, Ax is equal to lambda x. But what we can do here is this lambda, actually what you have to do is, you cannot, because A is n cross n, right? We know that A is n cross n, and x is n cross 1, right? X is n cross 1. So this I can multiply, no problem. But here I cannot, because this one, what is lambda? Lambda is a 1 cross 1 matrix. I mean, it's a scalar, it's a 1 cross 1 matrix, right? So now what do? We have to bring in front of x, we have to bring in the identity matrix, okay, and only then we can take this onto the other side. And when we do that, we have Ax, and when we bring it to this side, so we have minus lambda into identity matrix into x. Okay, now I can take x outside using the distributive property. I can take this x outside, and what will be left behind is A minus lambda 1. This is the identity matrix. So that's how we get this. Now by Cramer's theorem, you all are familiar with the Cramer's theorem. This equation number 5 has a non-trivial solution if and only if the determinant is 0. Okay, this determinant of this matrix is 0. So determinant of this is 0, and this is known as a characteristic determinant. And when you expand this, you will get a characteristic polynomial, and from there we can find out the values of lambda, and substituting lambda back, you can find out what are the eigenvectors. Okay, now next topic is the orthogonal transformations. But before we do that, let me just do a quick problem to show how this works. Very straightforward, very simple problem. So let's say I want to find eigenvectors of this one. Okay, to find the eigenvectors of this matrix. The matrix is a very simple one, a 2 cross 2 matrix, 1 minus 1 minus 1 1. We want to find this one. Okay, so this is your A. Okay, let's call this as A. Okay, so now what we need to do is we need to construct the determinant, characteristic determinant. So how do we do that? Characteristic determinant is the determinant of A minus lambda 1. A minus lambda 1. This is what we need to find out. So this is equal to, okay, A, what is A? A is 1 minus 1 minus 1 1. This is A. Oops, I think I should be doing it the other way around. We need to find out the determinant of, this is the matrix A, this is the matrix A minus lambda 1, the identity matrix. Identity matrix is 1 0 0 1. Okay, so this is going to give us, we are basically looking for this determinant. The determinant is 1, the first element will be 1 minus lambda into 1. Okay, and then this one is going to be minus 1 minus 0 is minus 1. Here we will have minus 1 minus 0 is again minus 1, and here we have 1 minus lambda into 1, which is 1 minus lambda. Okay, so this is what we have. So this is the characteristic determinant. Now from there we can obtain the characteristic polynomial just by evaluating this determinant, and from here we get, this gives us 1 minus lambda times, we are following this, okay, we're going like this. So 1 minus lambda times 1 minus lambda is 1 minus lambda square minus minus 1 into minus 1 is plus 1, and there's a minus, so this is what we get. So this is going to give us ultimately, I think if we manipulate this, we are going to get lambda into lambda minus 2. I had worked this out. You can try this out for yourself. When you open this up and simplify it, you'll finally get lambda into lambda minus 2. So now what do we need to do? Right, this has to be set to be equal to 0. So we'll do that next. We'll set this to 0. So therefore d lambda equals 0 implies lambda into lambda minus 2 is equal to 0, which implies from here, it implies that this lambda is equal to either 0 or it is equal to 2. Okay, so these are the two possibilities. So these are your eigenvalues. Okay, so these are your eigenvalues. So now we need to find out the eigenvectors. So how do you find out eigenvectors? We want to find eigenvectors corresponding to each of these lambda values. So for lambda equals 0, for lambda equals 0, we will write down this equation. The equation that we will write down is this. The equation that we will write down is a minus lambda 1, a minus lambda 1 into x is equal to 0. So this is a matrix equation that we will write down. So this gives us a minus lambda 1, okay, and a here is 1 minus 1 minus 1 1. So a here is 1 minus 1 minus 1 1, a minus, and what is lambda? Lambda is equal to 0. Lambda is equal to 0, and we have 1 0 0 1. Okay, and of course I have to put this inside the bracket, and then there is x. So this vector x, we could just replace it with x and y. This is equal to 0, 0. Okay. So now from here we have the first matrix. We have 1 minus 0 is 1. Then we have minus 1, because minus 1 minus 0. So minus 1 minus again 0 is minus 1. So it remains unchanged. So it will be a 1 here. And we'll get a x here and we'll get a y here. So this is equal to 0 and 0. Now let's do a matrix multiplication here on the left hand side. So when we do a matrix multiplication on the left hand side, what you get, x, right? X, 1 into x is x, and then minus y, and here we will get minus x, right? Minus x plus y. Okay, and this is equal to 0. I'm just writing it as 0. Okay, so therefore, if you look at this one, x minus y, okay, so what we really mean is this. When I say 0, we mean a 0 matrix. So 0 column matrix, 0, 0. That means this row must be equal to 0. So x minus y must be equal to 0, and also this row must be equal to 0. So minus x plus y is equal to 0. And from both of these, we get the fact, what we conclude is that x must be equal to y. So therefore, an eigenvector is, I should not say is, I should say could be. An eigenvector could be 1, 1. This could be an eigenvector, because in this case, you see, x is equal to 1. You could have other eigenvectors also. This also is an eigenvector. 2, 2. This is also an eigenvector. This is also an eigenvector. 3.7, 3.7. Basically, both of these values, they must be the same. Okay, but it's easier to choose the simplest one. The simplest one is simply 1, 1. So 1, 1 is the eigenvector that we are interested in. So likewise, you could also do this for lambda equal to 2, the other one. For lambda equals 2, you can see, you can work this out, and you'll find out for lambda equals 2, the other eigenvector that you will get will be 1 minus 1. 1 minus 1. Okay, so this is an eigenvector and this is another eigenvector. Okay, corresponding to the eigenvalues that we have. So that's how you can solve a eigenvalue problem. So with this, let me stop here, and then the next lecture I'll be covering orthogonal transformations. Okay, I'll be covering orthogonal transformations. For that, of course, I have to do some just recall a few basic concepts. So let's do that in the next lecture. If you have any queries, please let me know. Thank you.